Good afternoon. Today we will be talking about the primary paper, and its title is Dynamic Reconfiguration of Structural and Functional Connectivity Across Core Neurocognitive Brain Networks with Development. So first, it's important to know that understanding the dynamic reconfiguration of brain networks between childhood and adulthood requires identifying changes in structural and functional connectivity. The maturation of specific functional systems underlie the development of increasingly sophisticated cognitive functions from childhood to adulthood, including working memory, attention, and cognitive control. And these functions are implemented through interactions within and between a large scale of brain networks. So in past research regarding the networks, it's been found that structural neuroimaging has shown that while gray matter volume follows a regionally specific inverted U-shaped trajectory, white matter volume shows protracted increases with development. Also, DTI or diffusion tensor imaging, these studies have shown that anisotropy increases and overall diffusion decreases within age. So how structural changes impact functional brain maturation is less well understood. I think I pronounced that word incorrectly. It's anisotropy, but anisotropy measures describe the directional dominance of water diffusion within the region and within a voxel in the brain. Anisotropy provides an index of the degree of uniformity of water diffusion for a specific orientation. So next, we're going to go over the networks that were specifically involved. First, we have the Central Executive Network, or the CEN. And within the Central Executive Network, you have the dorsolateral prefrontal cortex and the posterior parietal cortex. And this network is related to the maintenance and manipulation of information and decision-making in the context of goal-directed behavior. And it's important also to know that this is a frontal parietal system. Next, we have the default mode network, or what I'll be referring to it throughout the paper as is DMN. The default mode network involves the ventral medial prefrontal cortex, along with the posterior cingulate cortex. And this network is associated with internally oriented and social cognition. So this is basically a network of interacting brain regions that's active when a person is not focused on like the outside world. You can also measure its activity with fMRI techniques. It's also important to know that this network shows lower levels of activity when we're engaged in a particular task, such as like paying attention to something specific, but it shows higher levels of activity when we're awake and not involved in any specific type of mental exercise. Next, we have the salience network, which contains the right frontal insular cortex and the anterior cingulate cortex. And the salience network is involved in attention as well as interoceptive and affective processes. So basically, it's involved in detecting and filtering salient stimuli, as well as recruiting relevant functional networks. So together, like and connected with the other brain networks, the SN contributes to a variety of functions like communication, self-awareness, and emotional and cognitive information. So still on the Salience network, this network includes nodes like the amygdala, the hypothalamus, the ventral striatum, the thalamus, and specific brainstem nuclei. And it co-activates in response to diverse experimental tasks and conditions, suggesting a domain general function. An important hypothesized function of the SN is to identify relevant internal and extrapersonal stimuli to guide behavior. So the RFIC node that's within the SN has been shown to initiate control signals that enable switching between the central executive network and the default mode network in response to cognitive demands, acting as a causal outflow hub, coordinating other large-scale networks. So let's talk about the causal outflow hub. In networks, hubs do allow for larger levels of information to flow between the nodes, kind of acting as integrators. So a causal outflow hub is a region that has a high number of causal outflow connections and a low number of causal inflow connections. And you can see this by using the Granger causality analysis, or as I'll refer to it in the paper, GCA. Excuse me. So during the performance of cognitively demanding tasks, the CEN and SN typically show increases in activation, whereas the DMN shows decreases in activation. However, what remains unknown is the crucial issue of how the operation of these networks identified in the resting state relate to their function during cognitive information and processing. So not a lot is known about the neural systems that kind of support the development from childhood to adulthood. And in this paper, they examine developmental changes in brain network interactions using multimodal imaging, combining functional and effective connectivity of intrinsic fMRI and DTI trajectory. And this includes data on how to show maturation cognitively, evidence of networks working together, and then the functional versus the structural connectivity. So next, they hypothesized that they would find differences in causal outflow from network nodes between children and adults. They also believed that there would be more dramatic changes with development detected in the RFIC, which is the right frontal insular cortex. And these changes would be further reflected in structural connectivity measures. So using functional and effective connectivity measures applied to fMRI data, they examine interactions within and between the Salience network, the central executive network, and the default mode network. So for their methods, they had 23 children and 22 IQ matched adults. And the children were 10 males, 13 females. Average age was about 7 or 8. And for adults, they had 11 males and 11 females. Average age was about 20. And just keep in mind that the adults and children's IQs were fairly matched. So data acquisition, these are the 3 types of data acquisition they use. For functional MRI, scan subjects were instructed to keep their eyes closed and try not to move for the duration of an 8-minute scan. And these functional images were acquired. For structural MRI, a high resolution TI weighted spoiled grass gradient recalled inversion recovery 3D MRI sequence was acquired to facilitate an anatomical localization of functional and DTI data. And the DTI data was obtained from 18 of the 23 children and 15 of the 22 adults. The DTI pulse sequence was a diffusion weighted single shot spin echo planar imaging sequence. So first, for data processing, for the functional MRI, a linear shim correction was applied separately for each slice during reconstruction using a magnetic field map acquired automatically by the pulse sequence at the beginning of the scan. Each participant's smooth normalized images were concatenated across time to form a 4-dimensional matrix. Each participant's smooth normalized 4-dimensional matrix was analyzed then with the FSL melodic ICA version 12, and then they define regions of interest and key nodes of the SN, CEN, and DMN based on the peaks of the ICA clusters. Next, for the results, in the first image here, we can see that they found that the RFIC connectivity with ACC and the RDLPFC and the PCC was stronger in adults compared with children. In addition, connectivity between the PCC and the VNPFC was stronger in adults compared with children. Thus, both within network and between network connectivity patterns were stronger in the older cohort. So they were stronger in the adults rather than the children. Next, they performed a GCA using a multivariate model on the time courses extracted from each of the regions of interest. In adults, this test revealed significant direct causal influences from the RFIC to ACC to RDLPFC to RPPC and then PCC. Excuse me. In children, the test revealed causal influences from the RFIC to the same regions except the PCC. Quantitative comparison of group differences in the strength of causal influences revealed that strength of interactions from the RFIC to the ACC and from the RFIC to the RDLPFC was significantly greater in adults compared to children. So again, in adults, GCA revealed significant direct causal influences from the RFIC to the ACC, RDLPFC, RPPC, and the PPC. And next, they used deterministic tractography to examine potential differences in structural connectivity between children and adults. Thus, adults had significantly higher number of whole brain streamlines compared with children. So this finding of generally increased whole brain structural connectivity with age is consistent with previous literature. To further explore potential factors underlying the functional and effective connectivity results, they examined structural connectivity between the nodes that showed both differential functional and effective connectivity between children and adults. A one-tailed Mann-Whitney non-parametric test was conducted to evaluate the hypotheses that adults would show greater structural connectivity than children. They found that compared with adults, children showed lower mean fiber density in the RFIC to the ACC tracks. So with that, future work examining all of these networks may reveal an even more detailed picture of changes in the network configuration and RFIC connectivity during development. Finally,